My name is Luís Barbosa. I have this double affiliation to the University of Minho and to the International Iberian Nanotechnology Lab, in which we have been implemented very recently a small research group on exactly quantum software engineering. And so this talk has a very humble objective. I just want to share with you some thoughts on how we think there is a need to have a clear idea of a roadmap for software engineering for the quantum domain. Okay, so as we have seen in Marco's talk, let me see if I can. Just a moment. Okay, so yeah. As you have seen just before, quantum is trendy. Research on quantum technologies is clearly speeding up with remarkable public investment all over the world. And for the first time, we are being able to discuss this very exciting area across real problems and across industries. In a sense, we are approaching the original dream of Feynman of letting nature suitably engineering to compute for us. Even if, as we have been discussing a moment ago, the project of a universal computer and a desktop quantum computer is still a very, very long way to go. Yes, quantum is trending, but the race is just starting. Clearly, if quantum computing will have a substantial impact on our lives and our societies, because it is really so radically different technology, it's quite difficult to anticipate its evolution. And we are, I would say, just doing the first steps in that direction. This graph basically shows the number of indexed publications in the area, which seems to be, on the left side, seems to be a very interesting curve. But if you compare on the right side with the curve on machine learning, for example, we see that we are just starting this very exciting move. Okay, so I think, and Marco clearly indicated much better than I some of these aspects, I think that this situation entails the need for four things. First of all, and I'm going to focus on that, for systematic effort to reorient research, both at a fundamental and an applied level, but also to a broad societal debate to explore and to assess the impacts of quantum on industry, on economy, on citizenship, on society. A massive training effort. Marco talked about industries getting ready for the quantum, and this involves, I think, quite a lot of refactoring of current practices and current algorithms and a massive training effort. And of course, related to that, the strategic involvement of leading companies and also as well as dynamic and young startups taking a very active perspective as technologies makers, technology actions, stakeholders in this area. So I would like to focus in this talk basically on the first aspect, on the need to reorient research. And again, I think it's quite consensual now that quantum computing is challenging. Finding new quantum and new hybrid algorithms is far from straightforward. Marco mentioned that, okay, we don't have so much quantum algorithms as one would expect from the outset. And on the other hand, the methods and the tools we have at our disposal now for developing quantum software are still highly fragmentary and still fundamentally low level. And even the circuit model is a very example a very good example of this. So what I mean by focus on this reorienting research is basically, and as always, to take the word science seriously when we talk about computer science. And I quote here not so recent communication by Vinton Cerf, by then the president of ACM, in which he said that we have the responsibility to pursue science in computer science. We must develop better tools and much deeper understanding of the systems we invent, and a far greater ability to make predictions about the behavior of these complex, connected and interacting systems. So please notice the magic words. Much deeper understanding, greater ability to make predictions about the behavior of complex systems, I could say about the behavior of quantum systems, and the better tools. And so our starting point, and the starting point of our work in my group is actually this understanding that the lack of trustworthy approaches to software development at the quantum level may put at risk the expected quantum advantage of the new hardware, the promises of the new hardware. And this actually lets us back to software engineering, because we understand software engineering as exactly taking very seriously this challenge. The idea is not new. You may recall, or some of you may recall, when we were discussing the grand challenges in the beginning of the century, there was exactly one of the grand challenges put up by Stepney and Abramsky and other people on exactly called the need for quantum software engineering, or an engineering discipline for the quantum domain. And almost more than 10 years afterwards, the truth is that although we have seen amazing development in the hardware and the availability of machines, of even real machines, when we come back to the software side, almost all key ingredients that we like to have in any mature software engineering discipline, like compositionality, abstraction, refinement, high order types, property enforcing type schemes, all these kind of things are completely absent, completely missing from the quantum landscape, or almost. So this is important, and the reason why I'm stressing the engineering, the software engineering in this as an umbrella to all these techniques, is the fact that by software engineering we mean something that is, as happens in other engineering disciplines, which is based on sound theoretical foundations that can actually lead to sound techniques in practice. So similarly to what happened in the classical case, we believe that quantum software engineering will greatly benefit from mature formal techniques, and by formal I of course mean mathematically based techniques that allow us to conceptualize and to predict the behavior of quantum systems, and to provide a framework, a practical engineering framework for their specification, development and analysis. So what I have in mind when trying to propose for discussion a roadmap for research in this area is basically this triangle, in which in the three corners I've written what I think are really challenges for any software engineering discipline, but in particular for the quantum case. The first is modeling. Which kind of models we have, which kind of abstractions we have to describe software, quantum software. The second is composition. If we have such models, how do we compose them? And how can we articulate this horizontal composition of models with a dimension of implementation that traditionally we call it refinement, and how these vertical and horizontal levels interact. And finally, verification. How can we specify properties? Because in software engineering, we don't deal with code usually, we deal with properties, we deal with specifications. How can we specify properties of behaviors, and how can we verify such properties for quantum software? So in the next few minutes, what I'd like to say is not to give answers to these questions, just to mention some topics around this triangle in which we have been working, and eventually propose them basically as an illustration, and nothing more than an illustration of these triangles. So in what concerns modeling, I think we still need, although there are already quite a lot of work done, and in particular this kind of work, this body of work developed by Bob Kuka and Abramsky and Vickery and their collaborators on what is called the categorical quantum mechanics, in which basically, I mean, at least in the long term, we will most probably provide an alternative to the traditional Hilbert space-based description of quantum systems. But okay, we already have such a framework and others, but the seek for appropriate semantic structures that can, for example, allow us to combine different types of classical control and quantum data expressed in a natural, mathematically sound way. And I'm written here as monads, because we know that monads, at least in the classical case, are able to capture several computational phenomena like non-determinism or probabilities, or even more recently, continuous evolutions of systems. And there are already some work on monads for quantum computation. It's a very nice way to encapsulate things and may provide a bridge between this classical and quantum world. And also, such semantic structures are heavily need to provide us with appropriate notions of program approximations, so program simulation, in which this sort of vertical dimension that I mentioned before can be analyzed. Models are also operational in the sense that they provide ways, they provide the semantics for program calculi, in which the systematic derivation of programs, of quantum programs in this case, can be done in a compositional way. We have been working basically in two areas in what concerns the quantum calculi. One is a calculus for static program transformation, or circuit transformation, if you prefer, to shrink the qubit lifetime, the need, the lifespan of a qubit, so that we can increase currents in a circuit. And also we are, another research line, we are discussing ways of enabling some forms of controlled iterations in quantum circuits, compiled from specifications to Qiskit. So models actually does not only provide semantics, but are able to provide syntactic calculi to reason about problems. The second dimension was composition, and I think this is really a main issue in quantum computing. Marco had a very nice slide on describing these components that can be reused from some algorithms to another, and I think this is really a crucial point. We may argue, at least if you are familiar with categorical quantum mechanics, that somehow an architecture of quantum program is already implicit in that framework. There are all the categorical structure around this sort of monadal categories that are used by in this setting actually provide several elements of an architecture for joining together quantum processes or quantum components. But in general, I think we are still far from having, from dealing with this in a more systematic and not in a more systematic way, but in a way that can be useful for the working software engineering. There are interesting approaches on developing process algebras in the traditional of classical process algebras for quantum programs. For example, to mix time, to incorporate time in a process algebra that mix classical and quantum systems to reason exactly about the NISQ architectures that we have been talking about some moments ago. On a very different framework, on the framework of coordination that in a classical computation has been developed by Farhad Ahbab, for example, in Rio, or and other approaches, but we have also been doing some experiments in introducing some sort of coordination mechanisms for quantum components. In general, the challenge, I would say, is to be able to move on these three axes that you see in the picture and somehow interconnect the horizontal and the vertical axes as usually expressed in sort of distributive laws that you saw you saw in the bottom of the slide. Of course, we have to give precise meanings to the semicolon and to this tensor, to this box, and this again calls us back to the need of appropriate models and appropriate mathematical structures for this. And the last dimension concerns exactly the properties and the specification and verification of properties. It's quite interesting that quantum mechanics from the outset, and even before we thought about quantum computation or quantum programs, actually has everything to do with the two axes that we use to reason about reality: logic on one side and probability theory on the other. So I think this is still a major challenge for us researching on this field. In particular, we would like to have for the quantum domain the sort of program logics, in particular dynamic logics, able to specify and to verify properties of algorithms. There is quite a lot of work on this, in particular the work of Alexander Baltak and Sonja Smets, but also Prakash and Wing and other people working on these areas. So I think there are very interesting results, even if partial in a sense. But again, like modeling and composition, this seems something very, very crucial for a discipline in software engineering for the quantum domain. Not only the ability to specify properties, but the ability to look for their verification in a compositional way. We have been, in my group, we have been working for some time now on developing what we call dynamic logics on demand. By on demand means basically that they are parametric, not only on the program constructors as they always are, but also on the structure of the truth space. Yeah, so we can have not only Boolean spaces, the usual Boolean algebra, but we can develop logics on top of probabilistic logic or fuzzy logic, or even paraconsistent logic, which is something that other researchers have been exploring as maybe suitable to express some phenomenon in the quantum domain. And from this sort of generic logics, we expect to develop OR logics, which can actually be used in the daily analysis of quantum problems. What can be achieved from a sound logic basis, program logic basis, that's at that level that I'm talking about, for the quantum program is quite a lot. One might think immediately on what all the contract-based development discipline means for quantum programs. In which way can we formalize the notion of contract, and in which way can we verify contracts for development of quantum software, as they are so successful in the classical case. Maybe on the other hand, that this could open the road for incorporating some assertions about noise in reasoning about quantum programs. this is, as Marco also mentioned, something very, very essential in the current state of affairs, and it will be for clearly for the years to come. And from a more theoretical point of view, I'm interested in identifying bridges between this sort of logical reasoning inspired in classical dynamic logics on one side, and the categorical quantum mechanics on the other, as a sort of a type theoretic form of quantum logic, if I can say so. So this was just a position paper, and I would like just to share some of these ideas and the things that we are doing. As a word of conclusion, I would say that for me, the ultimate goal of a software engineering discipline, either in the classical or in the quantum case, is the development of methods, techniques, and tools for analysis and verification and development of software in a formal way, and preferably in an automatic way, to the extent as it is possible. So just as it happens in the classical case, I'm convinced that quantum software engineering will greatly benefit from some mathematical foundations, and we are still working on them. That's true that a lot of theoretical work has been taking place since the 20s or the 30s on quantum mechanics, but in which concerns the foundations of quantum software, there is still a long way to go, I think. And this will happen, as it also happened in the classical case, in the confluence of several disciplines, mathematical disciplines, logic, algebra, category theory, topology, exactly as it happens in the classical case. And of course, from the lessons learned from the traditional, the classical software engineering practice. I think that we are in a sense living in the quantum case something similar to what happened in the classical one. Actually, we all know that the conceptualization of quantum computing predated for quite a long time its technological realization, and we are not still there at that level. So in a way, physicists are making it happen. But this was also true some decades ago with the classical machines. Turing machines anticipated digital computers for several years. So I think we are somehow living in a parallel way. But the difference is, and that's the message I would like to share with you, maybe for debate, the difference is that, differently from what happened before, we have now the chance to get the theory in place before technology emerged and popularized. So we have the possibility to start doing software engineering in a very precise way, in a very mathematically based way, almost from the outset. And this is a challenge that, at least for people who work on computer science and on this more theory-oriented part of the universe, is really a challenge that we'd like to take. So I think I was more or less able to keep in my time. Thank you very much for your attention, and I'm of course happy to take your questions. Thank you.
Yeah, thank you, Luís. We still have because we were late for 10 minutes, so we have a few minutes for questions. Anyone? Oh, I see. Yeah. Actually, I have the question because I read the paper. Even though it's in a talk, I didn't see you actually discuss this, but there was a very interesting comment section in the paper is talking about this quantum sensors and devices that integrated in the cyber physical system. do you actually have, any kind of comments on that, or you vision kind of applications actually in this direction?
Yeah, thank you. I mentioned that because for the last 3 years, we have been working on a monadic approach to cyber-physical systems in the classical case. In particularly, we introduced some new monads to encapsulate the continuous evolution as a continuous evolution of systems as a computational feature. And this works quite well in the classical case. And we are now looking at how this can be integrated with some of the proposals for quantum, for monads for quantum programs, in particular the ones introduced in Samson Abramsky group. Because as you know, the whole idea of monadic development is the ability to compose monads, so composing effects in this way. And we are looking at possible connections between these two monads that express such different computational phenomena. But this is something that is very much work in progress, and we don't have many very relevant results to report at that time.
Yeah, so looking forward for the results in the future then.
Yeah.
Thank you. Any other questions, anyone? Okay then, thank you, Luis, for the
Thank you very
great
much.
talk. Yeah, thank you.